Hi, I'm Casey Mulligan from the University of Chicago. I'm going to talk today about automated economic reasoning. Many theorems in economics can either be proven or disproven automatically with quantifier elimination. The economic reasoning package that I've made accepts the expression of reasoning in a format traditional to our field, and then automatically recognizes the theorem as a special case of Tarski's algebra. Using Mathematica's resolve function, the package eliminates quantifiers and then interprets the output. It's really my pleasure to be part of this conference, and I can personally convey my gratitude to the whole Wolfram team, for the amazing and useful products that they've put together. It really helped me do my job, and I really appreciate what you guys do. Now, this presentation is about automated economic reasoning. And all that Wolfram has to offer in the social sciences and related fields. Now, these are areas where computation has already for a long time been the norm for statistical analyses. But on the other hand, deductive reasoning, and by that I mean deriving conclusions from assumptions, has largely been left behind that computational revolution. And I had found this to be strange, because at some level I thought, how's deduction different than statistical inference that's long been done with computers? And sure enough, the technology's been available, but it's been a well-kept secret from those doing deduction, deriving assumptions from conclusions. So what I've built is a package that I hope or I intend to kind of get this secret out, as well as helping myself be an economics professor, write books, and do analysis of federal policy. The package does two basic things. First, it takes the abstract notation that's conventional in my field and recognizes it as nonetheless special cases of Alfred Tarski's nonlinear algebra. And that first step is where I think Mathematica was indispensable. I'm not sure any other software could have helped so easily to recognize the Tarski that's in everything. And then the second step is the deduction, to pass the Tarski problem to a nonlinear SMT solver or a quantifier elimination engine. And Mathematica has one of those engines. In fact, my experience, it's the most robust engine, quantifier elimination engine there is, and often it's the fastest, although not always the fastest.
Is that supposed to be on the slide?
Nope. That's just my cheat sheet. Okay, so anybody who's got Mathematica and connected to the internet can use my package. You just say get economicreasoning.com, and that'll download an M file, and you get a little welcome screen here. We're going to use some of the extras today. And then you could get started with Get Started, and you get a template that tells you, well, give me a list of assumptions and a hypothesis, and we'll look at whether that hypothesis can be concluded from the assumptions logically. Now, for a beginner, that can be intimidating. It's a blank slate. How do I fill in the blank slate? So I'm trying to help, and I've assembled quite a library of examples. If you click on examples, you'll get a pop-up which you cannot see, and I'm going to drag it over. When you're not in presentation mode, you get a pop-up like this, and I've sorted the examples different ways. For example, we have examples about many, many different things. The Laffer curve is one of my favorites. This first one's a problem I give the very smartest people in economics. I give them this economics problem, a real economics problem, and they mess it up, but the computer never does. Another one that I do is I do a lot of taxation analysis. We have a bunch of those. So these are all notebooks that you click, you can download, you can see how I filled in the blanks, and you can go ahead and you can type over that or be inspired to do your own thing. Now, to be clear, I'm not the engine here is not referring to the examples. It hasn't memorized the examples. The examples are just for the people to get introduced. Every problem is solved from scratch without any reference to these examples. So let's go back to the template. What's going to come out of here? Well, what's going on inside, I'm using Mathematica's resolve function, and that's amazingly powerful, to really do two nonlinear SAT SMT problems. The first question is there a counterexample? Is there a case when the assumptions are true and the hypothesis is false? So that puts you in a column. And the other thing it does is say, well, is there an example where both hypothesis and assumption are true? And then it's going to spit out one of these four results. So that'll be the output. We can try here the easiest economics example I could think of. So you don't have to rely on the machine, but you'll see that the machine gets the right answer. So in this easy example, we say price times quantity is expenditure. That's economics jargon. And then we're going to say, well, if the price were positive and the quantity positive, would expenditure be positive? Of course, that has to be true. There's no counterexample. We all know that, but let's see what the machine does. And it says true. There's no counterexamples. You also got another pop-up, which I'll bring over here, a dashboard that shows a little bit about what happened in the computation and some next steps. The next steps part, the different buttons, it's kind of like the Mathematica suggestion bar, same idea. Okay, so let's take a non-trivial example. This is from econometrics or statistics. It's about whether least squares estimates are biased and what conditions. So we're going to look at a kind of a regression setting here where we have a dependent variable related to two independent variables, x1 and x2, and an error term, epsilon. The coefficients are beta 1 and beta 2. So we'll put that in there. Part of the package, it calculates OLS regression coefficients. So if you ran an OLS regression in this setting, what would be the formulas for the coefficients? And those are the formulas. Now we're ready for a query. What we want to know is, well, this first OLS coefficient, do we expect it to be equal to beta 1? In other words, is least squares an unbiased estimator? What are we going to assume? Well, we'll assume that the first regressor is not trivial. It has some variation. And we'll assume that the x1 is uncorrelated with the error term. And what we want to ask the machine, is that enough to assume unbiased? If you've taken statistics, think to yourself what the answer is. It's not easy. A lot of advanced undergraduates get this one wrong. Some number get them right. What I want you to notice before we ask the machine, see what's in blue here. So the x's and the betas and the epsilons, they're in blue. So they're completely symbolic. I've not pre-programmed these things, the vectors, to be a certain length or to have a certain form or to have certain numbers in it. This is all abstract symbolic reasoning that's going on here. So now let's ask the machine what it says. Oh, and it says there's counterexamples. There's examples, but there's counterexamples. We're missing an assumption, in other words, or assumption or two or three. And let's see if we can figure out what those are. Before we do that, let's use the show space button, which is going to start to tell you how the package recognizes this as a Tarski problem. What variables does it view as critical for the reasoning? So we do that, and it found that there are six variables. Really, these are the elements of the Gramian matrix for the vectors, and it also says, hey, we recognize x1 and x2 and epsilon as being vectors. That all happened automatically. Again, this is not pre-programmed. It just knows from context that, oh, you must be talking about vectors here. That fact is going to come in a second here. Okay, so what else do we need to assume? Well, we just learned that there's not enough assumptions. So what else could we add? Now we're posing a question that's not true or false anymore. We're posing a question where the answer is a formula. What extra assumption do we need? So it's not in the SMT space anymore. It's not just a SAT question. It's a quantifier elimination question with free variables. That's a bit harder problem, but Mathematica does the harder problems. Many of the other software don't do that. So we have a button for that, but I'm going to do the typed version today. So theory sufficient with no arguments means take the most recent problem and tell me what assumptions I'm missing. So it's going to run. It found 4 possibilities. Any one of these 4 would be enough by itself as an extra assumption to make it true. So I found my users love this. When they're told that their proof isn't right, they always want to know, what do I got to add to it? And here's 4 answers for them, and they only need 1. Let's just check and make sure that the first one, for example, does it. And yep, sure enough, when you add the first one in, that's enough to guarantee that it's unbiased. Now there's no counterexamples with this extra assumption. Another question you might ask is, do I have too many assumptions? Are there assumptions that I could get rid of? Well, we got a button for that too. Let's try that. And it found a bunch of assumptions that could be dropped and it'd still be true. Now you might say, wait a second, how can there be a bunch of assumptions to drop? You didn't put in a bunch of assumptions. If a bunch means more than 3, what happened here? What's up with that? Well, the package recognized this as a vector problem, as we saw earlier. It recognized that the key reasoning is happening around the Gramian matrix for that vector problem, which is a 3 by 3 matrix. And so it automatically puts in restrictions that all Gramian matrices have to satisfy. It has to be symmetric and positive semi-definite. So you had extra assumptions that were thrown in here because it knew that you wanted them. It knows that you're reasoning about real valued vectors and therefore Gramians have this property. So again, you save yourself a lot of typing in by having that all done automatically for us. Okay, here's a different problem from labor economics. And if you take a look at the chart here, there's 2 series. One's gray with squares. Let's look at that one first. That's a measure of, probably familiar. I think New York Times has probably published this series 100 times or something very close to it. Shows wage inequality over time, over the years. And you know, in the 60s and 70s, wage inequality was pretty stable. But then we had this period of time in the 80s and 90s. Maybe it's even continuing today. There's more and more inequality. The gray square series keeps going up. So that's kind of the background. Now let's look at the black series. It seems to track it. But the black series is a measure of equality. So what gives? We have, every time we get more inequality, we also get more equality. What's up with that? And that, for a long time in my profession, that was viewed as a puzzle, a very curious puzzle. But I wrote a piece a few years ago arguing that, no, this is not a puzzle. The basic economics we use to think about wages and inequality would actually predict that the equality would be a consequence of the inequality. And I want to explore that reasoning here, here with the machine. So I'm going to define, probably very few economists in the audience, and it's okay if you don't follow each of the economic pieces here. I'll emphasize the computational pieces. But I'm going to define x. Again, this is all symbolic. X is something that happened over time. I don't know what it is. That's why I don't give it a precise name. I call it x. Name it anything you want it, I guess. But x is going to increase inequality, which is measured by sigma, without, this is a conceptual experiment, without changing the employment rate of women or the average potential wage of women. And so that's what I've defined here. What do I mean about x? It's keeping employment constant, it's keeping the potential wage constant, but it's increasing inequality. So we'll put that in. And then I'm going to be interested in, well, what's going on with the average wage of working women? H is going to refer to the average wage or human capital of working women, and x did something to that over time. And we'll be interested in what is that something qualitatively or perhaps even quantitatively. So that's kind of my setup. And then we need a little bit more setup to pose a query, a few definitions. What do I mean by employment rate? And this is when I refer to the kind of standard model in economics of wages and human capital. This is a pretty standard model. That's employment. This is, I'll put that in. The H is the average wage of working women. We'll put that in. Notice what's in blue here, meaning it's not pre-programmed, doesn't have any numbers. That's a joint. In our field, we interpret that as a joint probability density function. So what's going to happen when we start to do queries around this and it says true, that means there's no counterexamples. That means you could never find, you could look in the huge space of probability density functions, and as long as you can integrate it, implicitly it can be integrated, you're never going to find one that'll generate a counterexample to what we're saying. So that's what I mean by symbolic. One thing we want to refer to is positive employment, which just means P positive. And that there's some inequality in the baseline, that even back in the 60s we had some inequality, and what happened is we added to it. So that completes the setup, and now we're ready for a query. Which now we can check with this experiment we've defined, and starting from kind of baseline conditions with employment and inequality, is it necessarily true that the wages of women would go up, or would there be a counterexample, meaning we can't necessarily conclude that based on the assumptions? So we'll ask the machine, and it says true. There aren't any counterexamples. Now, I understand you probably didn't follow a lot of the economics because it's not your training, that's okay, but from the computational point of view, a couple things I want to say. First of all, the Tarski framework is a lot more applicable than you might first thought. Tarski's framework is usually described as polynomial algebra. But wait a second, I had dot products. I had double integrals. Those don't look like polynomials. But if you think of the problem in broad enough terms, it is a polynomial problem. And the package automatically recognizes those broad enough terms and turns it into that. So that's the first thing I want you to notice. The second thing you notice is these are real problems. I did not concoct these as toys for Mathematica to play with. These are things that I deal with and people in my profession deal with all the time. And the machine can do that. My real regret here is I wrote that paper, it's 11 years ago now. I wish I had the machine, because when we wrote that paper, we assumed a joint Gaussian distribution, which is a tragedy for two reasons. Number one, it's much more narrow. We just were reasoning about any joint distribution function that you can integrate, not just the joint Gaussian. And second of all, it was a big pain in the butt to do calculations with joint Gaussian. You can see the calculation is pretty simple. There's only a few basic things going in here. I really wish I had the machine. But better late than never, right? I want to say a few words about teaching, because I think that's where you start in teaching, not just economics, but computation. The young people are going to be the ones who are receptive and will take this somewhere. So what I do in teaching is, we can close this, done with this. I don't do proofs anymore. In the old days I used to, and my colleagues still do, drag students through step by step proving something. I just show them, hey, the machine said it's true. Trust it. Now, we don't stop there. What we do is repetition. I give them the machine and I say, look, there's the assumptions I use. That's hypothesis. You change it. You edit. You add assumptions. You take them out. You see what happens. And then they end up having a lot of repetitions. Instead of me dragging them through one theorem, they can do 30 theorems that are closely related. And then they start to get a different kind of understanding, and one that serves the comparative advantage of the people as opposed to the machine. So I've been very happy with that. The other thing that I think comes out of this is calculus is not a prerequisite anymore. A lot of people haven't taken calculus. A lot of college students haven't taken calculus, or if they did, they're not comfortable with it. And those are people who, in the old days, couldn't participate in my class because was how I was demonstrating a lot of things. But calculus, in most places that we use it, it's a shortcut. We're looking at the local linearity of the problem. So we're limiting ourselves to local problems so we can make them linear to make them easier. But why are we making it easy? Who cares? I don't have any mercy on this machine. Let the machine sweat, right? And so now you can pose problems without calculus, non-local problems, non-local comparisons. And my examples are all sorted that way. If you go through the example browser, I'll always explain, are we dealing with a local problem where calculus can be used? And I have to have that because my colleagues are so used to calculus. But what about the non-local problems? And there's a bunch of non-local problems that are really more interesting because most of life is a non-local change, not a local change. And then the students who are participating in this, they don't need to know calculus anymore because I'm not doing any local comparison. So that's pretty cool. So glad to take your questions, and I really appreciate all the things Wolfram folks do. It's very helpful.